Sorry. There you
Is it on? All right. Today, the big topic, and it's huge, it's called the chain rule. And basically, this is a rule that governs every derivative you will ever take, regardless of which calculus class you're in. Even in the higher levels when you have multiple variables, it's the same rule that always applies. See, we have come up with a whole bunch of derivative formulas so far, and they're really nice. We know how to differentiate the sine of x, the cosine of x, the tangent of x, x to a power. So every function you ever do, the thing you're working with, your argument will always be just an x. You're never going to have the sine of x squared, will you? You're never going to have a function raised to a power, will you? Or is the opposite true? No, you're almost always going to have stuff going on. You will rarely have just a single variable in a problem. So you're usually going to be raising functions to powers or taking sines and cosines of functions, meaning you're going to have compositions of functions the vast majority of the time. Well, our derivative rules we came up with only work if there's just one simple variable in the problem. But what if it's bigger than that? So let's do a simple example. All right, let's consider the following. Let's say that y equals, I'm going to do something small. Let's say 3x squared minus 2, okay, and I want to square it, okay? I want to find dy dx. Now, if I asked you to differentiate x squared, we know that's just 2x, right? I don't have to prove that. We proved that in class. I know that's just 2x. So the question is, if I differentiate 3x squared minus 2 quantity squared, would that just be 2 times 3x squared minus 2? Because when I differentiated variable squared, it was just 2 times variable. Now I'm asking you to do function squared. Does it seem reasonable it should just be 2 times function? Certainly that's a starting point. Do you agree? Well, I only asked you to do it to the second power, so let's square it out first. You remember how we did product rule last day? I asked you if the product of the derivatives was the answer. We realized it wasn't the answer. I gave you something small so we could see that wouldn't work. So we had to establish something. If I square this, what will I get? Think binomial squared. So first term squared, last term squared, and then 2 times first times last. That's the lazy way of doing it, right? I'm going to get this term here. So what is the derivative of that?
36x to the cube minus 24x.
Beautiful. And of course, that's exactly the same as, no, they don't really look all that close, do they? So, is this correct? No. Darn, I wish it was. Again, if it was, it'd make things so much easier. Well, it sure seems like this ought to be in the answer somewhere. What if I factor this? What's common?
12.
Yeah, so if I factor out a 12x, what does that leave me with?
3x squared minus 2.
That's a good thing in that I see a 3x minus 2 in that answer, don't I? Let me go one step further. What if I write it 2 times 3x squared minus 2, and then times 6x? Is that the same thing, first of all? Yes. Why did I write it like that? Now it kind of looks like that one, doesn't it? This isn't the answer, but is it part of the answer?
It's also multiplied by the derivative inside.
I'm sorry?
It's multiplied by the derivative inside the parenthesis.
Exactly. If I said, where does that come from in this problem? You'd say, that's exactly the derivative of that thing. This is what the chain rule is. It's literally kind of a domino effect that I differentiate kind of all the way through the problem. So I'm going to walk you through. But when we did this, I can always do this, and then I know I have the right answer. Are you okay with that? I can always do this. What if that exponent is really large? Do you want to do this?
No.
Oh, heck no. So you have to have a rule that works all the time, that doesn't require you to multiply everything out ahead of time. So as it turns out, the answer is this times the derivative of the 3x squared minus 2 part. That's what it turns out the answer is. Okay, let's do a similar problem. I want to differentiate 3x squared minus 2 to the, I don't know, 100th power. Well, I like to think of it this way. I want to differentiate thing to the 100th power. This is my formal mathematical language. I have thing to the 100th power. What do you suppose it's going to be? 100
Times.
thing to the
99.
99th. Am I done? Not quite. Now I need to differentiate thing. This was exactly the same amount of work as that one, wasn't it?
Mhm.
So did it matter how big my exponent was? No. It just mattered that I took this derivative.
All the way back there where it says 36x, is that a 3 or a 2? I really can't tell.
I'm sorry, on which part?
For the 36x.
Just a 3.
Well, you're differentiating 9x to the 4th, so it kind of has to be a 3, yeah.
Sure, thank you.
Yeah. So the exponent didn't make it harder, did it? But nobody in the right mind would have multiplied that out first. Do you agree? And here's the other reason why nobody in the right mind would have multiplied it out. The answer has to be in a factored form. So could you imagine somebody crazy enough to, spend a week multiplying this out? You'd have a lot of terms. And then after you're all done, you'd have to factor it again. That might be kind of hard. Do we agree that would be really hard to factor? Yeah, no, you don't factor it all, you just do it. So the formal way of writing it, there's multiple versions, but the simplest way of writing the chain rule is I start with a composition of functions. We usually think of it like this. Y is a function of, not of x, but another function. Like the sine of x squared. We're going to do exponential functions later, so we might do e to the tangent of x. I have a function of a function. X is still my independent variable, so the derivative is still dy dx, but dy dx is more than just f prime. When I did this the first time, that would be the f prime, wouldn't it? But then what's this? That's the derivative of the inside part. So what am I going to multiply by? That. And this is the chain rule. We're going to look at this later, but I could have a function of a function of a function of a function. I could keep going, and our chain rule would apply until I get to the inner variable. So we're going to practice this a lot. We're going to look at every version you could possibly have, and we'll see that every derivative formula that we come up with, it's really, really easy to automatically apply the chain rule. Okay? So, y equals the sine of x cubed. Question, is this the same as the sine of x cubed?
No.
No.
Some of us have gotten in trouble being careless with notation. What is the second one the same as? When I'm cubing the sine function, I put the 3 here. When I'm cubing the argument, I put the 3 after the argument. If I didn't put parentheses, does it change anything? No.
No.
No. Why do we put parentheses?
Make it more clear.
Good. I call it readability. It just makes it easier to make sure you didn't make a mistake. This is absolutely correct. We prefer this because it's easier. And there's no ambiguity, but it's always correct to use the parentheses. Again, no ambiguity, nobody could possibly misinterpret, but if the 3 is on the other side of the x, the sine function is not being cubed. The x is being cubed. I want to find the derivative of this. So I'll write it using the formal notation. That means I'm doing the derivative of this. Now, think of it as a door, and you're opening it into another room, and now there's another door. And you can open that door, and there could be more doors. But my outside door only sees the sine function. It doesn't see what's inside the sine function. Right? This derivative only sees the sine function. So the first thing I'm gonna do is differentiate the sine function, which gives me the
Cosine.
cosine function of the exact same argument. And I'll say this probably 157 more times. No matter what you do in math, the argument cannot change. There's no such thing as math that changes the argument. That's gotta stay the same. It never changes, right? That still showed up in the answer, it didn't change. That's the argument. If the argument is just an x, it makes everything easier, but the argument more often than not won't be just an x. So what do I follow it with? The derivative of, because now I said you got that door, now I'm gonna move to the inside, and I don't see an x, I see an x cubed. So I need to differentiate the x cubed.
3x squared.
3x squared, now where do you want the 3x squared to go?
Right in front of the cosine.
Probably in front, again, it's a readability thing. It just makes it easier. The 3 has to go in front. And funny thing is I teach calculus all the time, and half the time people leave coefficients in the middle or at the end. No, the term coefficient automatically implies it has to be in front. There's no such thing as a coefficient afterwards. That's not a coefficient. Right? The coefficient has to go in front. The x doesn't, but I think most of us, from a readability standpoint, we probably prefer the x there. The x could go afterwards. That's not a problem. But there's no possibility that I'm gonna ever misinterpret if I write it like that. Okay, you with me so far? That's not that hard. So now what if? I'm differentiating the sine of thing. What am I gonna get?
Cosine.
The cosine of thing, but don't technically I have to differentiate thing?
Yeah.
1.
So no change.
And that's just a 1. So are you technically using the chain rule even when you're doing an easy problem?
Yep.
Yeah, this is gonna be a 1. So we have a really clever name for this factor that shows up whenever I do the chain rule. Remember, this is math, so it's probably not that clever. It's called the chain rule factor. Yeah, I get it. That's the best we could do. You know, I want to give it a really cool name, like omega, you know, something cool. It's called the chain rule factor. Whenever you use the chain rule, you're multiplying. By the way, but chain rule factor, I'm not adding it, I'm multiplying it. If my argument is just an x, there is a chain rule factor, but the chain rule factor will always be 1. So do you ever need to show this? No, but technically isn't it automatically there? So what I'm saying is, every derivative you will ever take the rest of your life, there is going to be a chain rule factor. It's just it will sometimes be a 1, and we don't need to write that. So if my argument is just an x, the chain rule factor is just a 1, I don't need to write times 1. But if the argument is anything other than just an x, then I have to show the chain rule factor, or I won't have a complete derivative. It won't be correct. Okay? So let's do a whole bunch of things that look like this. All right, let's differentiate. How about I've got the tangent of x cubed? Huh. Is this chain rule?
Yes.
Yeah. One function's tangent, the other's the cube. Ooh. Now, you don't have to do this, but it might be easier for you to interpret if you wrote it like this. I'm asking you to differentiate thing cubed. So the outermost, what I'm seeing first, that first door is not the tangent function. That first door is the cube. And I know what to do if it were x cubed. I'd say it's 3x squared. Agreed? I have thing cubed. So what is it? 3 times thing squared. I'll go ahead and put the square here. Times the derivative of thing. We learned this last day. What is the derivative of the tangent function? The secant squared. Doesn't matter where I write it. I have the product of 2 trig functions. Does it make any difference which order I write them in?
No.
No, not at all. So I'll just do them in the same order they came. Multiplication is commutative, they're both trig functions, there's no advantage one way or the other. So that's my answer, that's it. Now, that's not that hard, but it is something to remember. You gotta remember this every time. Now, I want to differentiate, how about the secant of x to the 4th power? I'll keep it simple. So what is the derivative of the secant function? By the way, this is where I say, when I said print the sheet, this is a good time to have that sheet, so you quick glance.
X, tad X.
So secant, okay, are you guys happy with this answer?
No,
Why?
because we didn't differentiate the other bit.
No, way worse than that.
It should be secant x to the 4th times tan x to the 4th times the derivative.
I just changed the argument. Can't change the argument. Oh, good catch. That's why I asked if you were happy with that. Oh, by the way, will we do that at first? Yeah, at first we'll do that until we get the hang of it. Oh, shoot, yeah, my argument's x to the 4th. I can't change that. Now, have I ever differentiated the x to the 4th anywhere in this problem?
No.
No. Can I do it now?
Yeah.
Yep.
Can I just write 4x cubed?
Mm-hmm.
Sure.
I didn't write it in this form, but that's what I did. Now, as a final answer, do you like this?
No.
It's not wrong. Most of you would say I'd rather lead with the x cubed, but I definitely want to lead with the 4. So I'm going to put the 4x cubed in front. Again, it reads better. Secant x to the 4th, tan x to the 4th. And there's a perfect answer. Okay? That wasn't that bad, was it? Could have been way worse. I'm going to leave this up here. All right, now I'm going to ask you a question. Don't write anything down yet. What do you think? Some of you are nodding, some of you are shaking, some of you are doing the diagonal thing, which means interpret. Good or bad? Okay, I'm Caesar. You're the crowd, right? We're in the Colosseum. You have to make a choice. Are you going up or are you going down? You can't stay sideways.
Down.
He's going down. Why?
You didn't like keep the
Argument.
The argument.
yeah.
I took the derivative of the argument. Isn't that what the chain rule factor is?
Yeah, but
Mm.
forgot the
Chain rule factor.
Ooh, but it doesn't show up as a factor. I just did the only error that is actually common. Did I differentiate my argument? Yes. But I also replaced my argument with its derivative, which is not true. What did I just do? I just did f prime of g prime. That's what I just did. This is always incorrect, but this is by far the most common error because, wait a minute, I took the derivative of my function and I did my chain rule factor. But I did them at the same time and changed my argument. That's how you know it's not right, because I changed my argument. My argument has to stay this. That can't change. But aren't I supposed to take its derivative? Yes, at the end of the problem. So what should this read?
3 times that function times the derivative of it. Oh, the power check, yeah.
Now, the derivative of this is 12x squared. Where does that show up? Now, everybody got it? So I did take the derivative of my argument, but now I did it at the end of the problem. It's the last thing I do. It's the chain rule factor. The first thing I did was incorrect because I took the derivative and I replaced my argument with the chain rule factor. These are not the same. They're not really that similar. But it's an easy mistake to make at the beginning when you're first learning the ropes. Okay, and you can see why somebody might make that error. On the first exam, I'm going to ask some chain rule problems, and most of you will be, really easy time, and others will do the error because you didn't practice quite enough, or it wasn't absolutely clear. But this shouldn't be that hard, and we only have a handful of functions, don't we? Right now we have a handful of things. Okay, so, I'll do a weird one. What do you think?
It's the same thing as the other one, except,
Power to half.
you could just make it more readable by putting it in parentheses and doing to the power of 1/2.
Actually, I'd go way past readable, how it doable. He's suggesting I change it to an exponent, but you actually have to in order to do it. Do you see an exponent when you're looking at that? No, you see a square root, because it could have been a cube root. It could have been any root. I change it to an exponent first, not a derivative yet. Change. That's exactly the right thing to do. So my first thing that I'm going to do is rewrite this as quantity to the 1/2 power. Now, have I done anything yet?
No.
No, I expressed it in an equal manner. Roots and fractional exponents mean the exact same thing. But I can't do the calculus of roots. I have to have the fractional exponents, otherwise I won't know what numbers I'm dealing with. Now let's do the problem. I have thing to the 1/2 power. Its derivative is 1/2 of thing to what power?
Negative half.
To the negative half. And how did you get negative half?
Because it's 1, or half minus 1.
Half minus 1. Lest we forget, that's where it came from. Now what goes here? I'll write it out formally this time. I go back and forth. Now I want to make sure you see this. This doesn't get an exponent. I have an exponent on the outside. I went this to the negative half, and then I differentiate the inside. I've already dealt with the exponent. Now I'm dealing with the argument. So what does this part here come out to?
12x minus 4.
12x minus 4.
12x minus 4. Can I distribute the 1/2 into this quantity?
No,
No.
Why?
because it's to negative half. It's related to an exponent. You can't.
Because there's an exponent, yeah.
Yeah.
There's an exponent here. I can't distribute it there. Can I distribute the 1/2 into this quantity?
Yes.
Yeah.
Associative property, you can regroup any way you want. So I'm thinking about this as stuff to the negative 1/2 times 1/2 times this. I can multiply this times this. And why should I? Because these are both even numbers. Makes my life easier. Can you tell me the final answer now?
6x
Well,
minus 4.
is my answer going to be a product or a quotient?
Quotient.
Because
Minus
of the minus. So what's going to go on top?
6x minus 4.
Minus
I mean, minus 2, sorry.
Yeah.
Minus 2. Thank you. And what 2? Now, you have a choice. Do you want to write a fractional exponent, or do you want to write a square root, or does it matter? That's the first question.
It depends.
Does it matter?
It depends on what.
No. Does it matter whether you write fractional or root? Why? Because we said they're exactly the same thing.
Yeah.
Now, you get to choose. So what will dictate your choice?
If you're gonna keep using it, you probably want to keep to half. But if you're gonna solve it right now, you probably want to.
Yeah, I like that answer. It's not, maybe you were saying it depends on what I'm going to do with
Yeah.
it later. If this is the final answer, and I'm all done with it,
Oh, then it doesn't.
I think most of us would probably like writing just the square root, because there's no way I'm going to misinterpret it. Half is correct. But like you said, if I'm going to continue using it, maybe I want to leave it. Does not matter. So never feel obligated to change the fractional exponent back to the root. The only thing you had to do was move the negative downstairs. But you can leave it as a 1/2. There's nothing wrong with that. And it's totally okay to do this. So my answer is either this or the bottom raised to the 1/2. And they're the exact same thing. Can I do any canceling top and bottom?
No.
No, because again, the bottom's under a root, can't do anything. Now I said all derivative answers technically have to be factored. Is my numerator factored?
No.
Is there a common factor between those two terms?
Yeah.
2.
What's the common factor?
2.
2. So, if I wrote this, if I wrote my numerator as 2 times 3x minus 1, is that an improvement? Or is it basically the same thing?
Basically, it's like more writing too.
I said you always write a derivative in a factored form so you can determine where the derivative equals 0 by setting each factor equal to 0. So technically, that last thing I wrote, I'm going backwards. That is not a factored form. You said, but aren't you factoring out? Factors have to be things that can equal 0. Are you going to set the number 2 equal to 0? So in other words, if you're factoring out a constant, that is not considered a factored form. Is it wrong to factor out the constant? No. Is it absolutely in every conceivable way unnecessary? Yes. You never have to factor a constant out of something because you can't set the constant equal to 0. But if I had a really, really large constant, maybe for readability's sake, I might do it. This is correct. This is correct. This serves no purpose whatsoever. It doesn't get me closer to an answer. If I want to set my numerator equal to 0, that's just as easy as that. They're both right, but that's a constant. So I'm not actually factoring it because I can't set a constant equal to 0. A factorization is so I can solve that thing equal to 0. Everybody understands that? Ah, that's why.
Will you ask us on the quizzes and exam to factor it out?
No, it's implied.
Okay.
There is only one final answer to every question, and it is simplified first. That's the most important. Simplified. This is not wrong. It's just not finished.
Right.
But what if I had, hypothetically, what if I have a quadratic in my numerator? And you could factor it. Then you need to factor it because the very first application you're going to do is, where does it equal 0?
Right.
And if it's not factored, it's hard for me to tell. And sometimes it might be functions. Now, at first I will say, if it's possible to factor. I'll say that at first, because I want to get you guys used to it. But the farther you go in calculus, no one's going to ask, because you just know that's an automatic thing. Because you don't, this might sound strange, but you don't take derivatives just because they're really fun. Believe it or not, you don't just, I'm going to go home and just take derivatives today because it's so much fun. It's either that or, play with the dog. No, you take derivatives because you have a purpose in mind. You have a problem you're trying to solve, and the whole point of taking derivatives, the first question is always going to be, where is that thing equal to 0? And I'll relate it to graphs in a while, in a couple of weeks, but it'll make more sense the more problems we do. So it's something that you just get ingrained, you just get used to, okay? All right, let's do another one. A little bit more wicked than this one. Yeah, you're right. We're calculus people. We don't like things that look like this because we're not always absolutely certain how to deal with it. But the suggestion made earlier of using fractional exponents as a way of rewriting it is still what we have to do. But we have to have the correct fractional exponent. This should not take stages. I should be able to rewrite this in one step. My argument is this polynomial. So this is going to equal the polynomial
The power of -2
raised to a power.
-2 is weird.
Yeah.
How do you know? Because this is where most people have trouble. How do I know it's not 3 over 2? Everybody follow me? How do I know it's 2 or 3?
It's a cubed root, so it's over 3, and then the inside the function is squared, so it's 2 on the top.
When you have a fractional exponent, the root is always the denominator. When we did square root, our denominator was 2. I have a cube root, the denominator is 3. The 2 comes from right here. I'm squaring the cube root, so that means 2/3. But it's in the denominator, therefore,
Negative.
all right, I just rewrote it. Is this one now any worse than this one was? Those are basically the same problem.
Or
Same problem, isn't it? This didn't become harder, but if I don't do that translation perfectly, I'm doing a different problem, right? It's not gonna work. So this is the problem. So now when I do the derivative, walk me through.
-2x, and then put back the thing.
Negative 2/3.
2/3, right. And then put back the thing.
thing.
And then do d dx of thing.
To the power of
Yes.
negative 5 over 3.
Oh,
Negative
yeah,
5
negative
over
5 over 3.
So I have negative 2/3 and I'm subtracting 1, so it's negative 5/3.
Yeah.
Now I want to multiply it by the chain rule factor. This time I'm not going to write it out, let's just do it. What's the chain rule factor?
18x squared minus 24x.
And that's it? Does this get an exponent?
No.
No. At first, when we're just learning things, we sometimes cross over and do the wrong thing because we just did something else that seems similar. No, that's perfect. If I walked away right now, I have given you a correct result. Is it the most useful version of the result?
No.
No, there's a couple of reasons why. I definitely can factor this. I can do something with this. I got a negative exponent. Everything I said was correct, but I think we all agree it's not finished. In fact, my final answer probably has got to be a quotient, doesn't it?
Mm-hmm.
So what I'm going to do next, I can either factor this, or I can multiply the negative 2/3 in there. Doesn't make any difference.
No.
I'm going to have to do both of them at some point. What order do you want to do things?
Let's factor it first.
Okay, so I'm going to write this on the bottom, and what exponent am I going to put on it?
6.
5.
Positive 5/3.
Half of that, yeah.
What's common?
6x.
6x.
6x
3 times 3x minus 4.
Beautiful. Now, I'm almost done. I'm almost finished.
You have to multiply.
I've got it factored.
2/3. And
I have negative 2/3 times 6. Can I improve upon that?
negative 4.
Yeah, just write negative 4. That's an easy one. So negative 4 times x times 3x minus 4. My top is perfectly factored. Now, I've got this, or
Cube root.
I've got this. Now, what do you like better, the one on the left or the one on the right? I have my personal preference.
The right.
Do you like the left side or the right side's denominator better?
No.
My left.
Yes.
Are they the same thing?
Yes.
Yeah.
Someone said earlier, well, if I have to use it more, which is going to be easier to manipulate, left or right?
The left one.
Left. If I have to interpret what this actually means, which one's easier?
Right.
Right.
I got to use.
The left.
I've got to use a calculator. I got to do it on a computer. I can't actually do the one on the right.
Hmm.
Left.
I have to do the one on the left. You don't really. Do you have a key on your calculator that does cube root of things to the 5th power? No, but you have an exponent key which is in 5/3. Yeah. When the bottom was just square root, writing it to the 1/2, writing as a square root, we all had that one down. That wasn't even an issue. But I not only have a root, I have a root of something to a power, and this is when it gets kind of busy. This is correct. I think this is way easier in general. I would leave this as a fractional exponent every time, because again, I have a numerator and a denominator, I have to interpret it. The other thing is, the one on the left is a correct denominator. When I change it to roots, is there a possibility I mess it up? You know, that the root and the exponent get switched? Is that possible? Oh, it happens quite often, believe it or not. It really happens very often that I read it right in one, but then I misinterpreted it in the next. So I think leaving this denominator is more useful. This is the numerator exactly that I want. It's perfect. It's factored. If I ask you, hey, so anyway, where does this derivative equal 0? You'd say, well, it equals 0 when x is 0 or when x is 4/3. And there's a ton of information in that answer. It's all useful to me. Okay? So that one there we don't love because of the square root, but that doesn't actually make it hard. It just makes it kind of ugly. Okay? So far, so good. You guys kind of getting the hang of this? You said, this isn't the worst thing ever. Gosh. Okay. I want to take the derivative of the tangent squared of 2x cubed. This is different.
Rewrite it.
How do you want to rewrite it?
dx of 10 open bracket, 2x cubed, all squared.
Okay, I like that. And then in the strictest sense. So when I'm looking, what's the first thing I see? Do I see the tangent function or do I see the square first?
Square.
Square.
Then when I get inside that door, what do I see? The tangent function.
Mm.
But then when I get inside that door, what do I see?
2x cubed.
What's different about this one? This isn't f of g of x. This is f of g of h of x. This is 3 layers deep, isn't it?
Mm-hmm.
Ah, will this kind of stuff happen? Does that look completely crazy out of your mind, complicated, or does that look like something you might actually see a lot? Yeah, this is not that weird, but it's 3 layers deep. And if I don't see that, then I might not finish my chain rule. So this is always a good idea. That's the first thing. So this is 2 times tangent to the first power of 2x cubed. Now what am I multiplying it by? Watch. Times the derivative of the tangent of 2x cubed. I had thing squared. Agreed?
Also need the derivative.
So it's 2 times thing to the first power times derivative of thing. Okay, so now I have 2 tangent. We don't love this one because there's so much more writing. All right, the derivative of tangent, technically call it thing 1 and thing 2 if you want. The tangent of thing 2, what's its derivative?
Secant squared, or
The
secant
secant squared of
2x.
thing 2
times
times the
6x.
derivative of, oh
Squared.
my goosh. I had to do the chain rule literally twice, didn't I? Now, do you notice what I didn't do? I didn't write the answer as the derivative of tangent and the derivative of 2x cubed, because that's already taken care of within the chain rule. It's already, I don't want to write it a second time. Now, what is this derivative? I'm going to be really lazy. What is that?
6x squared.
6x squared. I don't want to rewrite this whole thing with that and then do it. I have a 6x squared, I have a 2.
Well, 12x squared. Times tan
2x.
and secant squared.
Are we good? Or is there anything else to do? We're good. Did I use product rule? Did I use product rule anywhere in this problem?
No.
Look at, if you just walked in the room and all you saw was my answer, how do you know I did not use product rule? What's missing? What's product rule? Something
Plus.
plus something, what don't you see?
No plus.
No plus. I did not use product rule. Should I have used product rule? No. Will people use product rule incorrectly? Yes. Because people see, they think they see a product here. This is a function of a function of a function. There's no product. I'm not multiplying anything here. So if I apply product rule, I'm going to get something else. That would be incorrect. Can you have product rule and chain rule at the same time? Yeah, that's the last part of today's class. That's the most complicated problem. We're going to have a product rule and a chain rule at the same time in a problem. That's sort of the king of the hill in terms of complexity. But if we can get through that, we can get through anything. Guys, everybody good so far?
Yeah.
Now, we derived the product rule yesterday, and it involved literally some cleverness. We had to add and subtract a term to the numerator. Most people wouldn't have seen that coming. Do you remember how we did it? Then we pulled it apart. Then we did all the manipulation, got the innermost limits, and did everything. It was kind of complicated. We got the result. And then we did the same thing for the quotient rule, and that might have been even a little bit more complicated, and we got the result. So you wrote everything down, you took perfect notes, you're getting ready to come to class, and a strong wind blew your notes away. And you're going, oh shoot, I can't even remember what the product, I got the product rule, but I can't remember the quotient rule. Wait, those dwarves, God, what were they singing again? And you start breaking out into Louie Louie. They didn't sing Louie Louie, they sang Hody Hi, Heidi Ho, remember? And so you're 5 minutes away from the exam and you cannot remember what the quotient rule was to save your life. Have I taught you enough to do the quotient rule today? Actually, I have. I have taught you enough to do it. I'm going to do it right now. You like this. This is not practical, what I'm about to do. This is not practical at all. You remember your product rule, but you forgot your quotient rule.
Yeah, put the power of -1.
G of x to the -1.
G of x, how about to the negative first power? Now, is what I wrote true?
Yep.
Is it better? No, not in general. If it's a quotient and I need to use quotient rule, use quotient rule. I mentioned before, if your denominator's raised to a power though, you're gonna find, and we're gonna do this today, that writing it as a product with a negative exponent is actually convenient. That is true. Let's do the product rule on that one. But we're also gonna have to apply the chain rule. I couldn't do this last day because we didn't have the chain rule. So, according to product rule, it's first times the derivative of the second. But the second is thing to the -1 power. So what do I do?
-1
-1
times G of x
thing
to the -2.
to the -2 times the derivative of thing, which is
G prime.
g prime of x. I know that's true because that's what we've been doing for the last hour. Right? Function to a power, power function, power -1, derivative of function. That's the chain rule factor. But it's product rule, so now plus the second times the derivative of the first. So what's the derivative of the first?
F prime.
Yeah, f prime. One of the things we like about using this type of notation is just f prime. I don't have to think about what it is. I just write it out. And now there's my quotient rule. That really doesn't look much like it. Oh, but I have negative exponents. I have common terms. -2, -1 power, which is the common factor.
-2.
Yeah, always the more negative is the smaller. So I'm gonna factor out a g of x to the -2. And now what does that leave me with? Leaves me with this times this times this. So how about if I write that as negative f of x times g prime of x? Okay. I factored out to the -2, so doesn't that leave a whole g of x here?
Yes.
Okay. We're almost done. I don't like that -2. So let me move that downstairs. How about? Negative plus. Could I write that as this and then subtract that guy? Would that be legal?
Yeah,
And now what?
that's quotient.
That's the quotient rule. You like that? Was that easier than doing it using limits?
No, wait, yes.
Probably, yeah. Well, why didn't we do this yesterday? Because we didn't have chain rule yesterday. But now that we do, you go, wow. There's a lot of the functions and a lot of the things that we derive that when we learn new tools in the future, we can go back and say, you know what? I just found an easier way to do something. And that's actually a good thing. But it also is a beautiful thing that it confirms what we already knew. So if I forget, now I say this in all seriousness, you're doing something. Maybe you're not home. Maybe you don't have access to the materials. And you're working a problem, and I need you to take the derivative of the tangent function. You're going, oh shoot, I can't remember the derivative. Can I change it to sine over cosine and use quotient rule? Yeah, that's how we derived it. You can always go back and do that. Now, that's not efficient. Remembering the result is better, but what if you forget the result? You know how the result was derived in the first place. You can always go back and figure it out. And a significant amount of the material that we cover, it's going to be exactly like that. You can go back and figure it out because you have enough tools to fill in the blanks. See, what if you were absent? Remember last day, the recording stopped. So the quotient rule, did the quotient rule make it to the video? I don't think it did. No, it's on the Zoom lecture, but if somebody was relying on that and they say, oh shoot, I don't know how we derived it. Well, you can do it that way. It's kind of powerful. Okay. Let's see, let's do d dx. Now this is weird. This is not something you see very often. You don't often see trig functions under roots. You might see trig functions to simple powers, but this one is kind of different. Do I want to rewrite this one?
Yeah.
Yeah,
Yeah.
I think I want to rewrite this one. How would I rewrite this as?
Sine
Sort of
x
half.
to the half.
To the 1/2 power. Does that trouble me? No, could I put literally any exponent there on planet
Yeah.
Earth? Yeah, and I'm gonna do exactly the same things in the next step. I'm gonna bring the exponent down, and then it will be the sine function raised to the
Negative half.
And around
negative 1/2 power times the derivative of what?
sine of
Sine.
The sine, not the sine to a power, just the sine. My argument is just the sine function, so times
Cosine
cosine. Have we given a correct answer?
Yeah.
Yes.
it's not finished.
Do we have a finished answer?
that. No.
Now, we addressed this last day. I mentioned to you, if you are correct but you're unfinished, you're not wrong, you're just not finished. I think we would all agree that that's not finished for only one reason, the negative exponent.
Mm-hmm.
The fractional exponent is fine, it's the negative exponent that we don't like. So, what's gonna stay on top?
Cos x,
What do you wanna put on the bottom?
2 sine,
2 root sine x, probably.
2.
I'd probably go with the root. I think that, yes, I can do 1/2 power. But in this case, it's just a square root, pretty clean. If you wrote it to the 1/2 power. Now, question. Question. I'll put 3 question marks. Can I do that?
Yes.
No.
Wait, no.
No. Can I do that?
Oh, no.
No. I can only do this with positive integers. I can't do it with fractions, I can't do it with negative numbers. Problem is, it crosses over with ambiguity. There's other things that are represented that way. So when it comes to trig functions, if I have sine squared, all right, sine squared, I'd rather not write parentheses, it's too much work. But if I have the square root, I gotta write the whole thing to the 1/2 power. If I'm doing a function, keep it really simple. I have, this function to the 3rd power. Can I write it this way?
No. That's the 3rd derivative.
Yeah, good catch. That means it's the 3rd derivative. Oh, remember we talked about derivative notation? Yeah, no, I actually would have to do this. Yes, it's a pain to use all the extra parentheses, but the nice thing is there's no possibility anybody's gonna misinterpret my intent. A lot of times when we're doing things, they'll take liberties with the notation because it worked for trig functions, but it only works for trig. There's other things that we're gonna do, like logarithms and other things, where we wanna put exponents in places that they really can't go. And it will confuse. And if I wanted to do it, type it into the calculator or something else, it might confuse the calculator. So, yeah, it's a headache, but I gotta do that. It may be a headache, but I can't do that. I gotta put it on the outside to the 1/2. Definitely can't do it with the negative exponent. In fact, -1 means inverse. It does not mean reciprocal in any context. So there's misinterpretations because I will actually write a function that means something completely different if I misuse the notation. Don't want to do that. Don't want to make mistakes on purpose. Okay, I'm going to take a break now. I'm going to do the roll. When we come back, we're going to look at some problems that are a little bit busier, but thank you. Okay, these are the calculus formulas from the first half of the course. These are all derivatives because you notice everyone starts dx. Now look at the very first one. What do you see? Derivative of u times v. Shouldn't that be product rule? I mean, I'm asking you to differentiate a product. What's weird about the product? What's missing? I'm asking you to do d dx of u times v. There's no x's. Does that feel weird? It should, except this is the universal way of doing things. We shorthand the notation just to make it easier. U and v are functions of x. So I'm doing the product rule. First times derivative of second, plus second times derivative of first. That's exactly what it is. When you write y, we've been doing nothing but x and y so far, agreed? And all of our y's have been functions of x. We're going to do that for a little while because I don't want to go off on too many tangents yet. How often do we write y of x? Have you ever written y of x? No, you write y, it's implied that it's a function of x based on the way we're working the problems. The d dx means that x is the independent variable, therefore everything else has to be a function of x. So when we do dy dx, that's our derivative. That means that y is a function of x. But do we ever write y of x when I start the problem? We did earlier today, we did things of this nature. We did y equals, sine of x. Technically, shouldn't I really be writing it like that? Because if we said f of x, we'd write it that way. Does anybody write it like this? Seriously? No. No, it's implied y is already a function of x because I have that. I'm differentiating. So u is a function of x, v is a function of x. But just to make it a little easier, rather than writing as the first thing, I want you to all differentiate u of x times v of x. Well, when I established this last day, I did f of x times g of x. It's the same thing, isn't it? But instead of writing u of x over and over and over again, we're just writing u. We're writing v. So now look at it again. Oh, it's first times the derivative of second plus second times derivative of first. That's exactly what we did in class. But now look at the next one. If that u is actually u of x, then what's the derivative of sine of thing? It's cosine of thing times the derivative of thing. You see it? That's the chain rule factor. So every single one of these formulas, I don't have functions of x, I have functions of u. It is implied that u is a function of x. So when I'm doing my chain rule, I'm taking the derivative that I already know. I know how to differentiate sine, cosine, and tangent of x. But what if it's now sine, cosine, and tangent of function of x? Same derivative, but then times the chain rule factor, which is the derivative of that function. That's why every single one of these ends with a du dx at the end. That is the chain rule factor. This is what you're going to do on every derivative you ever take. Now, it looks complicated at first, except we just spent over an hour doing exactly that, didn't we? We did it for the 6 trig functions and x to a power. So now, the function that we started with our derivatives on, the very first one we learned was this. And we know this is true. Now I'm saying we're going to kick it up a notch, as Emerald would say. That is not a variable u, that is a function. That's u of x. So now think of this as thing to the n. So what's the derivative? N thing to the n minus 1 times the derivative of thing. And this is exactly what we've been doing. That's the chain rule. Does that make sense to you now? So every one of those is the derivatives we're going to learn. We're going to learn each derivative one at a time as just a simple function of x. So we're going to do e to the x and log x and all these things. Then once we establish our regular derivative formula, then we're immediately going to take it up to, okay, now what if it's a function? What if it's not just an x, but it's a function of x? Then how does it change? Well, don't these two formulas look identical right here? Yeah. The difference is this has a chain rule factor. Does this technically have a chain rule factor? Yeah. It's right there. We just don't bother writing times 1. But I need to know this version because this is the general case. This is specific to only that function. This is for all things. This is better because it's always true. So this is the formula sheet I said I want you to have with you at all times this semester. You're not going to memorize this as you go, but by the end of the semester, you're actually going to know most of it pretty well through repetition. First day of Calc 2, you are expected to know every part of this. There's a lot of formulas on here. Why? Because that's now considered incoming knowledge. So if I don't know how to take all my derivatives going into Calc 2 or all my antiderivatives, I'm kind of in trouble. But you have time. Again, repetition. You're doing things so many times in a row. You're sitting in a differential equations class. It's really your 4th semester of calculus. You know these pretty well. As long as you haven't taken too much time off from your other calculus classes. That does happen sometimes. I teach Calc 2, and it's not unusual. I'll have people in a class that's been 10 years or more since they had Calc 1. Life got in the way. Changes of plans. But they can't retake Calc 1. So for them, it's a real struggle because they don't remember these, so they really have to go over and review and review and review. You guys, no. You've got a few weeks off at Christmas, and then you're going to kick it right up again. You're not going to forget all this stuff. It will be ingrained because you will do it over and over again. But if you have it in front of you, it's so much easier to keep track of. Okay? So that's what I was referring to last day. Last day it looked kind of nonsensical, but now that we see the chain rule, we realize, oh, that's why we write it like that. I just don't like writing u of x, v of x over and over again. It is absolutely correct to write u of x raised to the nth power. And then I need another set of parentheses or two. You see why it gets kind of cumbersome in the writing after a while. So let's get on to the next thing. Okay, now we're going to start looking at problems that are just a little bit bigger. That's a product. I want to find the derivative. It is a product. Am I going to have to use product rule in this problem at some point?
Yes.
Mhm.
Yes. No way around, no shortcut. And I certainly don't want to expand either one of these. Those exponents are too big, too inconvenient. In fact, I don't want to expand it because I don't have to factor it out later on. So, if it helps you, there's your u, there's your v. Or like lastly, there's your f of x, there's your g of x. So according to the product rule, I'm going to do it the long way. According to the product rule, it should be first times the derivative of the second. Have I taken a derivative yet? No, I'm writing out what I'm going to do. Plus the second times the derivative of the first. Okay? Haven't taken any derivatives yet, but now I'm done with the product rule. Okay? Thing to the fourth power. Walk me through.
Times 4 times 5x plus 2 cubed times 5.
Times 5. 5 is the chain rule factor of the 5x plus 2. Perfect. Am I done with this stuff here?
With that side, yeah.
I'm done with that stuff there. Plus. Not doing anything with that guy. Thing to the sixth power.
So it's 6 times 4x squared minus 3 to the power 5 times 8x.
Are we happy with this so far?
Yeah.
We're done. We're done with the calculus. Calculus is completely finished.
Finished algebra.
Now, is that a useful final answer to anything?
Yeah,
A little bit too busy. I'm done with the calculus. The rest of the problem is going to try to make this thing a little more concise, a little less busy. Because don't I have common terms on both sides of the sum? Can everybody see that? I have common terms on both sides. I have this to a power, this to a power. So I definitely want to factor this. Because I can write my final answer in a factored form. I can write my final answer as a product of terms. So I just have to figure out what do I need. So I clearly have a 4x squared minus 3 to a power in both terms. I clearly have a 5x plus 2 to a power in both terms. What exponents should I use? Okay.
The lowest one.
So what exponent's the
5.
best one? 5. Exactly. Okay.
And then a 3.
3. And then what's here is everything else. Any questions so far? Again, we're done with the calculus. The busiest part's now the finishing of the algebra. Yes.
How did you get that part for, I wasn't here the day you did the lecture, so I don't know how you got to that step. The 4x squared minus, okay, so I understand that, but would you, I can't see past this side.
Which, you said
Where
that
the
part.
5 and the 6 and the 8x are, where does that come from? No, below, yes.
6
Oh, I
quantity
see.
to the 5th. This is today's lecture. This isn't the previous lecture. This is what we did today. So this,
Oh, I knew it. Oh, okay, I see now, thanks.
if it were x to the 6th, you tell me the derivative is 6, x to the 5th.
Oh,
This
right,
is
that's right.
thing to the 6th, so it's 6 thing to the 5th, and then that's called the chain rule factor. Yeah, derivative, yes, but that's kind of vague, but chain rule factor specifically. I'm done with the calculus, no more derivatives. So now, look at what we pulled out. I pulled out all of this and all of one of these, all but one. 4 times 5
20.
times one of these,
Mm-hmm.
yes?
So,
So
yep.
20 times a
4x.
single 4x squared minus 3.
Plus 48x.
Okay? I pulled out all of this and all but one of these, so I have one of these left over times
48x.
48x. Now, if I do this right, notice that both of these are to the first power. Sometimes we make mistakes and I'll have too big an exponents. Why are they both to the first power?
Did you get
Because
that?
whatever the original powers were, one of them kept it and one of them decreased by exactly 1. So they have to only differ by 1 at the most. So when I'm factoring out the common factor, I can't have exponents larger than 1 because they only differ by 1. Now, I'm almost done. Can we make this a little bit prettier? Can I make that into one polynomial?
Yeah.
Yeah, but I'm going to need to distribute.
Mm.
So how about 80x squared minus 60 plus 240x squared plus 96x? What does that leave me with? That's what, 320x squared plus 96x minus 60. Now, obviously there are constants that are common to each term. Do you agree there's constants that are common? But that's really not the question.
Hmm. Oh, great roots.
Can this be factored? I can factor out a constant, yes, but it can be factored as the product of
I don't
binomials.
think so. No.
You sure? I'm pretty good at factoring, but those numbers are kind of large. If that can be factored, I really want to factor it. But if it can't be factored, by the way, this is going to have 2 real solutions no matter what. But I only want to factor it if my solutions are rational. I don't want to factor if my solutions are hideous roots. Because I can just use my quadratic formula for that, can't I?
Mm-hmm.
So in the strictest sense, can I leave this alone? Yes. Let me give you a what if. What if this factored beautifully? You know, 40x minus 6 and 80, or let's say 8x plus 10. It isn't. But look at the numbers. What if it factored like this? I would want to do it because now each of these is easy to work with. I'm going to ask you a question. How do you know if it's factorable or not? This is something you learned in remedial algebra, and at the time you learned it, it probably made no sense to you because you never used it then. You only use it in calculus and above, I find out, in my experience. I'm going to remind you of something you have seen in ancient history, but I'm going to show you how to use it so it can become useful to you again. I have, and by the way, this only applies to quadratics. I have a general quadratic. There are 3 possibilities. Well, think about if I were factoring. Could I have a perfect square? Is it physically possible this could be a perfect square? In which case I get 1 repeated root. I could get 2 real roots, or I could get 2
Unreal, imaginary.
complex. Imaginary is part of complex, but complex is not going to be imaginary. So how do I know? Well, what does your quadratic formula tell you? Remember this? This is good to know. This is remedial algebra that we use in calculus and above pretty often. What determines whether my solutions are real or complex? That part right there. If that's 0, then I have a perfect square. I have 2 repeated roots because I'm plus or minus 0. If that's positive, I have 2 real roots, and if that's negative, I have 2 complex roots. You with me? Now, because these are different in sign, this is gonna definitely be positive, because the minus 4AC is positive. No big deal. I'd like to know if it's factorable. So, does anyone remember what this is called? There's a word, starts with an E. Discriminant. Yeah, this is actually a very important math word. The discriminant is the b squared minus 4ac part. Not the square root of that, no. Just the b squared minus 4ac. And it only has 3 possibilities. We don't like this one because it means I have 2 complex roots. This is kind of like saying I have a parabola that opens upwards, but it's entirely above the x-axis. Right? It's never going to intersect. This is like saying I have the parabola that opens upwards and the vertex is on the x-axis. This is like saying the parabola opens upwards but starts below and crosses twice. 2 real roots. I'm only interested in this one. Okay, so let's all do that for this problem. Let's calculate the discriminant. This squared minus 4 times this times this. Let's all do that. It's not very hard.
Negative 67,000.
It should be positive. It should be positive. 96 squared minus 4 times 320 times negative 6. Really big positive.
86,016.
86,016. That's huge. Now, that means I have 2 real roots, but they could both be, and they're probably both irrational. They're probably ugly square roots.
Yes.
How do I know if I get happy answers or not? This is either a perfect square or not. If your discriminant is a perfect square, then what happens when you take its square root? You get a nice happy integer. Am I right? If your integer is not a perfect square and you take the square root, you get an ugly root. It's one or the other. Take the square root of 80,000 or 86,000. Do you get integer or ugly decimal?
Ugly.
That means you had 2 irrational solutions. That means we would not consider this factorable. That means I can walk away from that answer. What if? What if you took the square root on your screen and it turned out to be a perfect square? Then it means the factorization is actually really simple and you could easily get through it or use your quadratic formula if you had to. But if that was a perfect square, then it means I'm not done. I can easily factor this, and then I should. I got 2 irrational solutions, so I'm going to leave this alone. What if I'd gotten a negative discriminant? Well, I definitely am leaving it alone. I don't want complex solutions. It is going to commonly be the case that you get this down to a quadratic, but you may not be able to factor it because of the sheer size of the numbers. But you have other means. The fact that my discriminant was not a perfect square means I'm walking away. There's no reason to keep going. But Mr. Wren, you can factor out a 4. Wow. Does that make my life any easier? No. Factoring out a constant isn't worthwhile, isn't necessary. So, what is the best answer I can give? I'll rewrite it. And order does not matter, by the way. I've written it in a factored form. I can tell you exactly when this is 0. I can tell you exactly when this is 0, and I will use my quadratic formula to tell you when that is 0. So that's the best answer I can give. Does it matter what order I write those factors? No. Now, there's some humongous observations I need you to see. I don't want to tell you. Look at the original question. Did I just give away the ending? Look at your answer. Do you notice anything? Look at the problem, look at your answer. Somebody?
That whole thing is just the chain factor?
Well, no, the last part definitely involves a chain. But look at your factored answer and look at your original question. Do you see anything?
This is the same, except for the power.
They're both 1 lower, so they've
They're
just.
both 1 lower. Both of your exponents decrease by exactly 1. Coincidence? Hardly. No, that's absolute. Is that a good thing? I took the derivative of something raised to a power and my exponent decreased by 1? Yeah, but on both of them it decreased by 1. That's very powerful. Quick error check, isn't it? I have a final answer and the exponents didn't decrease by exactly 1 each. I think I probably have an issue there, right? I might have a problem.
Can you go over again how you got like the first part, the blue part? Because I'm not understanding how you
This
got
part?
it from. Yes,
Yeah.
I don't understand that.
So when I'm looking at my big picture here, I have stuff to the 6 and other stuff to the 3rd, blah, blah, blah. Do I have any common stuff? Yeah, let's start with the 4x squared minus 3 term. I got it over here to the 6 plus I have it over here to the 5th. It has a common factor, and this is the common factor because it's the smaller exponent. Now I looked at the other big ticket item. This is raised to the 3rd, this is raised to the 4th, so that's the common factor. That's why I put it here. Okay, so that's like baby algebra when you're factoring the common factor. Now, the stuff on the right is just what's left. This is everything that is left. Then I just cleaned this up a bit. The only remaining question is the stuff that's left, can it be factored? In this case, we saw no, it can't. Sometimes you suppose it can be? Yeah. You don't have any control over that, you're just trying to discover it. So our final answer is the derivative of the original, but in a factored form, which means it's now in the only usable form that I could have. If we left it like this and you needed to determine when is this 0, when is this positive, when is this negative, you couldn't tell me. Right? This isn't useful as a final answer, but it's the calculus. So, you guys good with this?
For the 48 though, I don't understand why it's 48x multiplied by the 5x plus 2,
Well,
because it's multiplying the 4x squared minus 3.
I have this times this times one of these.
So you just switch the 2? Because on the
No,
other side
no.
it's 4 times.
I factored all of this and all but one of these, leaving one of these a 6 and an 8x. It's right here. 6 times 8x times one of these is right here. And then on the other side, I factored out all of this and all but one of these, leaving one of these times a 4 times a 5. You're not seeing it.
It's okay, I'll figure it out.
No, but that's not the part we should have trouble with. That's the part I'm just taking what's left when I pull out my common factors. But I need to pull out the biggest common factors, otherwise the stuff remaining is going to be too busy. Now, I need the room, so I'm going to start over here again. Now this was, fun. This was beautiful. What if? Big ugly quotient. I want dy dx. Ooh. All right, well, I guess we'll use our quotient rule. We can. It will take exactly twice the writing that one did. And the simplification, well, we'll probably most of us just throw in the towel, change our majors,
Rewrite it.
Your sociology is still taking people, right?
We put the denominator on the top of that negative
Right as a
5.
product.
Yeah.
Yes, you can use it as quotient rule. It will take you a minimum of double the steps, and it's extremely unlikely you'll have, it's so much longer, and it's so much harder. We're gonna write it as a product. I mentioned this last time, I mentioned it earlier today. When your denominator is something raised to a power, always write it as a product. But then it means, what about my exponent?
There's negative.
It's gonna be negative. By the way, in the last problem, did the size of our exponents have anything to do with our strategy in the order of things?
No.
No, we just, whatever exponent was, we worked with that exponent. So if I rewrite this in this form here, isn't this exactly the same problem that we just did?
Yep.
Yeah. The fact that I have a negative exponent, it's an exponent. Nothing changes in my approach. So let's use the exact same strategy we just did. So when I want dy dx now, I'll write right here. It's the same thing. First times the derivative of the second. Careful. What's the derivative of the second?
Negative 5 times 3x plus 4 to the power of negative 6.
To the negative sixth, yeah. The arrow, sometimes we go the wrong direction when we see a negative exponent.
Times 3.
Times the chain rule factor of 3. If I forget that 3, is it a big deal?
Yeah.
Yeah, it will actually change my answer. And it will change it enough to where the zeros and things won't be the same. They won't really be similar. I'm done with the left side. Plus 3x plus 4 to the negative fifth. And now let's differentiate the other side. So I'm differentiating 6x minus 5 to the 9th power.
That's 9 times 6x minus 5 to the power of 8, and then times 6.
And then the chain rule factor of 6. Okay, from a calculus standpoint, what's next?
Simple math, no more calculus.
There's no more calculus. I'm done. I did the product rule and the chain rule within the product rule. I'm done with the calculus. Everybody got that? Now it's just gather terms and clean this mess up. So we're going to do the same thing we just did,
6x.
one term at a time. Now, can I go ahead and say I'm going to have a 6x minus 5 to a power and 3x plus 4 to a power? Can I say that safely?
Yeah.
Yeah. I don't know what powers yet. I got to figure that out.
Maybe 8.
But one thing that is absolutely certain, these differ by exactly 1. These differ by exactly 1. So when I pull out the smaller of the two, it'll use that one up, but it will leave exactly 1 factor on the other side. Just 1. Okay? So,
Will that factor always be positive then?
I'm sorry.
Will that factor always be positive then?
Well, it'll leave out, yeah, up to the first power. That's why we have to pull the smaller, which is never an issue when both numbers are positive. But we have to think a little harder when both numbers are negative, because I might go the wrong way. If I said between 9 and 8, 8, nobody's thinking about that one. Do you agree? Between 9 and 8, 8 is the common, this to the 8th power is the common factor, and it'll leave 1 over there. But between negative 5 and negative 6, which is the smaller?
Negative 6 is small.
Negative 6, and that's the one we sometimes, if we're not thinking about it. So do you agree that negative 6 would be the common factor?
Yes.
Which will leave exactly 1 positive term here, to the first power. So I'm going to have 1 of these left over here. All of this got used up. All of this got used up. It's going to leave exactly 1 of these. Okay? And the other stuff, just go along for the right. The coefficients, basically.
Negative.
So go slow.
Negative.
I used all of this. I have a 3 times a negative 5
Negative 15.
times 1 of these. So I have negative 15 times 1 of those. Plus. Over
54.
here, I used up all of this. I have a 9 times a 6 times 1 of these.
54 times 3x plus 4.
Here's what I really like about the one on the right. It's a linear factor. I don't have to worry about quadratic, it's linear. Boy, that one's, doesn't matter what my coefficients are, that one's really easy to work with. So, this is gonna be negative 90x plus 75 plus 162x plus 216. So all together, I'll do it like this. What is this reduced to?
So you feel that's plus 291.
72x plus 291.
Okay.
Hmm.
I don't like that.
So put it underneath this equation.
Put it downstairs. I'm gonna put that one first this time. I'll put that one second. Okay, now what? Are we done?
Mhm.
Ooh, okay.
And order on the top doesn't matter.
Doesn't matter,
Okay.
product. It doesn't matter, and it's not even about readability, but a lot of times people want the bigger exponent after it. I did it purposely the other way around last time to show you it really doesn't matter because it's a product. But it does matter about that thing downstairs. Now, remember the rule we had a moment ago about the exponents? Did we just violate that rule? No.
No.
Because when I rewrote it as a product, both of these did decrease by 1, didn't they?
Yeah.
When I rewrote it as a product, they both decreased by 1, but I had to put it back downstairs when I was all done. I want to make sure you guys see that. So that is the derivative of the original statement. Is it busy? Yeah. Is it hard? Not necessarily. Okay, it is, I can easily make mistakes by going too fast, right, being careless, but for the most part, that's not too bad. Are we good?
Yeah.
Okay. Don't want to lose any more material. Okay, any questions on this so far? Is this the worst of the worst of the worst?
No.
Probably not. Probably
can't
just
be.
like this one.
There's got to be something worse than this. We did a product of things involving positive integer exponents. Then we did a quotient of things involving positive integer exponents, which means it was really involving some negative exponents, negative integer exponents. Can you think of something worse?
Non-integer exponent.
Such as,
Fractions.
exactly. Oy. What if I do the same kind of question, but instead of positive integer exponents, I'm actually doing roots? Yikes. Okay, there's still time to change your major, right, and run for the hills and all that kind of stuff. Let's look at that problem. I'll do it as a product rather than a quotient, okay? So I've got y equals, I'll keep it relatively simple. So I got 3x squared minus 2 to the, I don't know, 5th power times, how about 8x cubed plus 1 to the 3rd power. We just did this. Ooh. Yuck.
That's crazy.
It's out of control is what it is. Right, it's just like all hell breaking loose, dogs sleeping with cats, the whole 9 yards.
These are gonna make them much worse though.
What do we do?
Split it up.
Rewrite it.
Put it all down.
Okay, rewrite it, but be very specific. How?
Open brackets.
Okay, that's my part.
Put that all in brackets. All
Not
in
yet.
brackets. To the power of a half.
The square root of a product is the product of the
3
roots,
and-
true or false?
3 and 1.
True. So technically, I'm gonna be, technically, can I kind of think of this as being square root of this times square root of this?
Yeah. 3 and 1.
5 over 2, and then 3 over 2.
Was that hard to rewrite? Was that hard to rewrite?
No?
No, but I really had to be paying attention, didn't I? No. By the way, the most important part is not the answer. Convince yourself that you actually believe that that is true. Not, I'm doing it because Mr. Brown wrote it. He hardly ever lies to us, you know. Is it true? The square root of a product is the product of the roots. So 5th power square root is 5/2. We know that's true. Now, can I do this problem exactly the way I did the previous two?
Yeah.
Exactly. But now those fractional exponents can make things a little bit wonkier. Yeah, Cece.
Did you just combine steps for that part?
Not necessarily. It's reading it because it's square root of a product. I have product of the roots.
Okay.
Yes, it would have been absolutely correct for me to write this as root times root and then do this. And that's not incorrect. But it's a little redundant if you know that was a legal move. I'd rather you do that. If you're not sure, do that, then do that. We got to get to here at some point. Agreed? So let's take this one now to the bitter end. This is about as bad as it'll ever get. Because everything we did before, and we're throwing in the fractional exponents. But in the end, the only difference is this answer might have fractional coefficients where the other had all integer coefficients. Does that make it all of a sudden way worse? Not really. As long as I recognize it really is the same thing. So, dy dx is first times derivative of the second. What's the derivative of the second?
3/2 times the thing to
Power
the
half.
minus.
To the positive 1/2, agreed?
Yeah.
Yeah, but positive 1/2. Good.
Times the,
And then what's the chain rule factor?
24x squared?
24x squared, good. The derivative of 8x cubed plus 1 is just 24x squared. Why isn't it plus something? Because the derivative of 1 is
0.
0. Derivative of a constant is 0. So lest we forget, oh, that's why there's not a second term. Plus. Now I have the second term to the 3/2 times, now I want the derivative of this part.
5/3
5,
over 3. No, half.
the
sorry.
5/2, yeah.
Uh,
That'd probably be better.
times the thing,
Good, a thing to the what power?
3/2,
And then the chain rule factor is
6x.
times 6x. Just like before. We're now done with the calculus portion of the problem. Now the rest is the god-awful simplification. But is it really that much worse?
No.
Not really.
It's mostly being mindful that, okay, I have fractional exponents, just be a little bit careful, but just like before. These two outer ones, the exponent differs by exactly 1. These, the exponent differs by exactly 1. So when I pull out the greatest common factor, I will always be left with one of them's gone, the other has an exponent of 1. Not a fractional exponent, mind you, but an exponent of exactly 1. And I like that. That truly makes me, feel warm and fuzzy on the inside. All right. So I have 3x squared minus 2. I have 8x cubed plus 1. Now, 3/2, 5/2. What do I want to use?
3/2.
3/2. I have 1/2, 3/2. Which one do I want to use? 1/2. I always pick the smaller. If you choose the larger, you can still do the problem, but you're going to end up with something in the denominator, and that's way worse. Really hard to work with.
3/2 times.
Okay, so now let's go back to here. I've got 3/2 times one of these times 24x squared. I'll write all out. So how about 3/2 times 24x squared
Right.
times 3x squared minus 2. Does that look right? I have exactly one factor left over times 3/2 times 24x squared. Plus, now the second part.
5/2 times.
I pulled out all of this, so I have one of these left over. 5/2, 6x, and then a one factor of 8x cubed plus 1. Okay? I'm not worried about the stuff on the left. That's easy enough. And you know what? When I distribute here, I think we're not going to have any fractions.
No, we don't.
What's 3/2 times 24?
Squared.
So that's 36x squared.
It's 15x.
What's 5/2 times 6x?
15x.
Okay, I'll just go right there. Now, let's go and distribute. This will be, what, 108x to the 4th minus 72x squared?
Cool.
Yes?
Yeah.
No? Maybe? Okay, yes.
90? No.
15 times 8,
That's 100.
120x to the 4th
20 plus 15.
plus 15x. Well, the x to the 4th certainly certainly combine.
So it's 228x to the 4th minus 57x squared.
Okay, so I have 228x to the 4th minus 72x squared plus 15x. Well, that's not a quadratic, that's a 4th power. I don't think I'm going to be able to factor that. I don't think it's even possible that I can factor that, is it?
No.
No.
Does anybody see anything there? There's no way I'm going to factor this, right?
You can pull out an X.
Doesn't everything have an x in it?
Yeah.
Yeah, I can definitely pull out the x. Now, what's remaining, the cubic that's remaining, probably can't do much with, but the x, I definitely can factor that out. So what is this gonna be?
X times 2 to 8 x cubed minus 72x plus 15.
Beautiful. Can we now express our final answer? We almost have it right there anyway. So now here's the question. Leave the fractional exponents, change them to roots.
Underneath.
What do you want to do?
uh,
Leave the fractions or change them to roots?
fraction.
Before, when we had a 1/2, we were changing it to a square root, which is absolutely correct. But here's what I wouldn't do. I wouldn't change this one to a square root and then leave this as a fraction. No, either both square roots or both fractional exponents. Or what someone said, could I put the whole thing under one big root?
Yes.
Yes.
Is that necessarily an advantage?
No.
No.
Yeah.
You've got to work with, this is physics, this is something else. And this answer you actually have to work with. You have to evaluate, you have to do it on your calculator. Which version do you think is going to be easier to work with, that one or the second one?
The second.
Yeah, I think the second one's going to be much simpler to manipulate. Having all of this stuff all under a root, I think, is just a little bit messy enough till we could get lost. These are absolutely identical, but I needed to do this for the purposes of differentiation. We got an answer that still looks in that form. It is absolutely correct to change it back to that form. I don't see an advantage. I think leaving it in this form is better. Plus, I don't have to change anything. I can walk away. Remember, if your two answers are the same, whether it's a root or an exponent, then whatever your last version was, just walk away. Right? You can't make a mistake if you don't tweak it, if you don't change it. So the best final answer is probably, now, it doesn't matter what I write first, but maybe I'll write that one first. This is about as bad as it can get. But we were able to navigate through all parts, weren't we? Now, when I say as bad as it can get, from a rational function point of view, right, polynomial-ish things. I didn't do this with sines and cosines and other things. We tend not to do as much with the exponents for those guys, but that's correct. Okay, any question on this? Again, if you can follow this all the way to the bitter end, you're in pretty good shape on your overall understanding. But taking derivatives of polynomials is much easier than anything else. Polynomials are our favorite creatures to differentiate, right? Because I just have to consider the exponents. Now let's look at something else on the icky side. Because we haven't done this one in a moment or two. I don't have any fractional exponents, I don't have any quotients. This is just pretty straightforward.
It's a product.
It's definitely a product, so do I have to use product rule?
Yeah.
Will I have to use chain rule?
Yeah.
Yep.
Where?
Sine
This
squared.
feels good.
Because it's a function squared. I won't need to use chain rule on the cosine of x, that one's pretty clean. But on the sine squared, because it's function squared, there's definitely a chain rule there. So we've all been instructed, we have to use a chain rule, we have to use a product rule. Do I have to choose the order of things, or is it kind of automatic? I need it to be automatic, because if I have a choice when one really doesn't exist, I could easily go the wrong way. Whereas I know they like to say in physics, I won't quote the professor, but when it's a 50-50 proposition, you will make the wrong choice about 90% of the time. By the way, I'm a mathematician, that's actually a complete fallacy, but I love it, because that's what they say in physics. You ever heard that one? I won't say who says it all the time, but I know who says it. Yeah, if it can go either way, you're going to make the wrong choice 90% of the time. So we're going to do a coin flip, heads or tails. You're always going to pick wrong 90% of the time. No, but I don't want a choice. I want to know there's one dictated path. Okay, I got to do the product first because it's a product of functions. It's not a chain rule till I get inside. So it's first times derivative of the second. What is it? We just learned this.
Negative sign.
Negative the sine function. Good. Plus the second times the derivative of first, and this is where the chain rule comes in. So the derivative of the first, I'm differentiating thing squared. How do you differentiate thing squared?
2 sine x times cosine x.
2 thing to the first times the chain rule factor. Beautiful. So far, so good?
Mhm.
All right, so here I've got negative the sine cubed plus, does it matter whether I write sine cosine or cosine sine? Does it
No.
matter what order I write them?
Nope.
No, absolutely does not. What order do you want to write them?
By sine cosine.
Okay, we'll write sine cosine. So 2 sine x cos squared x. Beautiful. Am I done?
Yep.
Almost.
There's a factor.
I have a common factor, don't I? What's my common factor?
Sine.
Sine.
Sine. Yeah. Now, because the sine is my common factor, I have a negative term plus a positive term. That is absolutely correct.
2
But most of us would rather write positive term minus term, wouldn't we? From a readability standpoint, if I said to you, the final answer to the question is negative b plus a, that's correct. But wouldn't most of us say, you know what, I think it reads better if I write it like that. It doesn't change anything. But most of us would rather write it in this order. It does not matter. But if I write it in that order, then I'd have 2 cos squared x
minus sine squared x.
minus sine squared x. Or I would have said negative sine squared x plus 2 cos squared x. So there's a question you should be, it's burning through your brain right now. What should be, can I
Cosine squared x minus sine squared x is like 1.
do anything with that? Hopefully that question is just burning through. You're not going to be able to sleep at night until you answer that question. Well, there are Pythagorean identities I can apply. I can change the cosine squareds in terms of sine squareds. I can change the sine squareds in terms of cosine squareds. Does it necessarily give me an improvement if I do? I'm going to show you both. And you may decide that this is the final answer you want. Okay? We know that cos squared plus sine squared, as long as it's the same argument, which it is, we know this is 1. So that means we can replace cos squared with 1 minus sine squared. We can replace sine squared with 1 minus cos squared. The reason you would do this is if I had to set this equal to 0, I cannot set this equal to 0. I'm pretty good at this stuff. I can't set this equal to 0. Why? I have 2 different functions. Oh, so if I need to figure out where this is equal to 0, I really only want one function. So let's say I want all cosines. So I'm going to replace this with 1 minus cos squared. And there's a negative in front, so what does this become? It becomes sine x times 3 cos squared x minus 1. Because it's the negative of this plus this. This is an absolutely correct answer. This might be more useful because it's not very hard to set that equal to 0 and solve. Or, what's the other choice? Replace cos squared with,
Sine squared minus 1.
other way, 1 minus sine squared. In which case, I'd have 2 times this minus a sine squared. So I could have also written it as 2 minus 3 sine squared x. I think, is that right? Or did I lose something? 2, yeah. And again, easier to set equal to 0. That might look prettier, but I think it's safe to say that both of these would be more useful if I was trying to set it equal to 0. Do you agree? Can I somehow squish it into one term? I really wish I could just do one thing. Nah. The different coefficients kind of prevent me from doing that. If I have a cos squared plus sine squared, boom, Pythagorean identity. What if I had a cos squared minus sine squared? Would that be useful? Yeah, that's actually a biggie. We reviewed that on day 1. Cos squared minus sine squared, there's another identity there. Remember what it is? It's the double angle formula.
1 minus sine.
No, if I had cos squared theta minus sine squared theta, that's the cosine of 2 theta. And I would rather work with that guy because there's only one term. I almost have that, don't I? But the mismatched coefficients. So the mismatched coefficients really prevent me from making this. So this is the answer. Walk away. I need to use this to do more later on. This is going to show up later in a problem. Maybe it's in my physics problem. I have to do more things with it, including potentially setting it equal to 0. In which case, I probably would prefer one of these two forms. By the way, is there an advantage of one of these over the other? Not really, because I got one trig term and one constant, so it's the same amount of work in both of these. Everybody cool with that? All right, yes.
I have a question from the beginning. Where did you get the 2 sine x times cosine x at the end? I don't know why I
Oh,
didn't
okay.
see it.
First times derivative of second.
Yeah.
Second times derivative of first. Well, this is function squared. So what's my derivative? Thing squared. So what is it? 2 thing to the first power
Oh,
times the derivative of
Okay.
thing. I will always use the formal mathematical language when we're doing this, so you don't get caught up on the specific function. You say, what did I just do? I did function to a power, derivative is power, function to the power minus 1, derivative of function. I'm calling that thing. And as long as I do that, I'm going to get the right answer the vast majority of the time. Yes, you're going to make mistakes. Make them now, not later. You're going to make mistakes. That's okay. It's just don't make the same mistake repeatedly. This will require practice. We have 7 specific functions now that we know the derivatives of, right? We know x to a power and 6 trig functions. But now we know all the composition ways of doing it. So we know function to a power. We know trig functions of other functions. We have product rules. We have quotient rules. We have a whole bunch of stuff. And we still have the vast majority of all the formulas, or functions, I should say, remaining in the course that we have to figure out. Whoa. Okay? It's a lot more involved, but the chain rule is something we're going to do on every problem. That's why that's all we did today. Okay? Questions? Okay, go ahead and stop that.